So, say a couple more things about conditionals when it comes to talking about these things in words. Let's go back to one statement that we had last time. If it rains, then I will bring my umbrella, which we can represent as if P then Q. So this particular sentence is not the only way to express this as an if-then statement, at least not the only way in words. What's another way that we could say this? No, see, if I bring umbrella then it rains, that's a different statement. Okay, but we can put it in the structure of Q if P. This means the same thing, it's just grammatically speaking you've sort of moved all your phrases around. So, I will bring my umbrella if it rains. You're still saying if P, it's just that you've said that second instead of saying it first. Does that make sense? So this is exactly the same thing. This is almost kind of a grammar lesson. Okay. You can say P implies Q. It's raining implies that I am bringing my umbrella. That means the same thing. So now I want to take a look at this statement in order to show you another way of thinking about this. If it's a dog, then it's a mammal. So do we agree with that statement? I hope so. Okay. So this will let you see another way in a situation like this where you're describing objects. There's another way to say if P then Q. All P are Q. So how can we restate this in that language? All dogs are mammals. Now, of course, you couldn't apply it to the previous one. You couldn't say all rains are umbrellas. It doesn't make any sense. This refers specifically to when you're describing objects and their properties. Okay. So P is Q. A dog is a mammal. That's just plural versus singular, really. Okay. So now let's go the other way. All baseball players are athletes. Now go back and rewrite this in terms of if-then.
All players are athletes, then they're baseball players.
Sorry? Yes. If you're a baseball player, then you're an athlete. We're making statements about there are two objects here. We're making statements about them. Okay. Now, how can we draw a diagram of this? Well, typically you'd have, and by diagram I mean a Venn diagram. Typically you'd have, okay, so you need to be able to represent athletes and non-athletes. What else would you need to represent?
Baseball players.
Baseball players. So typically, how would we do that? You have the universe in two circles. But that's not what we draw here. Because what do we know about baseball players? They're all athletes. So it's a subset, exactly. So we would not need to draw it the typical way, because we know that the set of baseball players is completely within the set of athletes. Now, equivalently, you could just draw it the first way and then put a. And what could you do? Equivalently, you could just put a 0 over here, showing that baseball players who aren't athletes, there aren't any of them. Okay. But we're showing how to represent this in the most simple diagrammatic way. Okay. What about the statement, some basketball players are professionals? How would you represent that in terms of a Venn diagram? Yeah, then you do the regular thing. Exactly. Right. Because by this statement, you have among the basketball players, which is set B, and then you also have the circle for the set of professionals. Some basketball players are professionals. That's where it overlaps with P. And then some are not professionals. And then that's the part that's outside of P. So in this case, you have both. Does that make sense? Now what about this? No Major League Baseball players are minors, meaning under the age of 18. Now how could you represent this on a diagram? Would you draw two overlapping circles? Two circles not overlapping, exactly. Okay. Now, when we make pictures like this relative to statements and qualities, they're also called Euler diagrams. So granted, yes, Euler diagrams and Venn diagrams have some things in common. Okay. But is it clear why you can draw two circles separately? Okay. Well, let's look at the circle for Major League Baseball players. So if you're in that circle, which is M, then are you a minor or not? Okay. But is it possible to have... I'm sorry, I flipped it around, sorry. Okay. So if you're a Major League Baseball player, then the way the diagram is drawn, can you be a minor? No. But what does the statement say? Exactly, that's what the statement says. The statement says if you're a baseball player, you're not a minor, and that's what the diagram reflects. That you can't be in both at the same time.
So, can we say that this diagram represents the subset would be every time you say the word all, that would be a diagram as well. The Venn diagram would be called the
Yes, unless there's other stuff going on. If it simply says all this or that, then yes. If it says some this or that and no this or that, yes. Then you can draw it like this. Okay. Now, all kids go to school. Everyone in school has a favorite teacher. What can you conclude?
All kids in school have a favorite teacher?
Basically. So, just make a statement about kids. All kids have a favorite teacher. So the idea is we're sort of jumping over the school part just to make a statement about kids, and we're making the connection with favorite teacher. So does that make sense? Now let's draw the picture for this. So how can we draw the picture for this? Okay, so what's a subset of what? So what should I draw a circle for? For all kids. Okay? So I'll draw a circle, K for kids. Now, what's the next circle that I should draw? Teacher circle, and where does that go? Okay. So we'll call that T for teachers. Now, does this show that all kids have a favorite teacher? If we want all kids to have a favorite teacher, how does that have to be reflected in the diagram? Yep. So let's actually back this whole thing up. Okay. So first we draw, let's actually go statement by statement. All kids go to school. So if this is the circle for kids, the next thing we should draw is the circle for, I'll say go to school, I'll just call that S. How do we draw that circle? Absolutely. Just like that. Okay, so does this represent all kids going to school? Absolutely. Now, everyone in school has a favorite teacher. How do we draw that? I draw a circle for favorite teacher, and how do I draw that? Because we want everyone who's in the S circle to also be in the favorite teacher circle. Because that's what we're saying. Anyone who's in school has a favorite teacher. Does that make sense? Okay. And so now when we look at the picture, what can we clearly see? Everyone who's a kid. Right. So we already know that everyone who's a kid goes to school because that was one of the givens. But we can conclude, which wasn't given, everyone who's a kid has a favorite teacher. You just look at those two circles. Does that make sense? On a cold day, I wear my fake fur coat. It is a cold day. What can I conclude? I'm wearing my coat. Okay. Now, how can we draw a picture to represent this?
You gotta get fake fur coat.
Okay. So here's a circle. I'll just put C for coat. Oh no, I can't do that. That looks like cold. Okay. So I'll use FFC, fake fur coat.
And then on a cold day, you draw it like over, around.
Okay. So Terrell says that I should draw this for cold day. Now, is this telling me that on a cold day I'm definitely going to wear my fake fur coat? Can I have a cold day where I'm on this picture? Can I have a cold day where I'm not wearing my fake fur coat? Right there. What's happening at that dot? And and it's a cold day.
So you put the circle inside.
Yep.
Yeah.
Okay. So what we have is, this is a cold day, and this fake fur coat. Because if you like, another way to interpret the given statement is, for all cold days, I wear my fake fur coat. So that should give you an idea as to, regarding which circle goes in which. What about this one? On a cold day, I wear my fake fur coat. It is not a cold day. What's the conclusion?
He's not gonna be first circle.
Is that automatic?
Wow.
You say on a cold day you wear the coat, it's not a cold day.
Uh-huh. Is it possible to have a day that is not cold where I'm wearing my fake fur coat? Look at the picture. Is it possible to have a day that is not cold where I'm wearing my fake fur coat?
Yeah.
Okay. So this is what we were talking about last time. This is the fallacy of the inverse. If it's a cold day, then I wear my fake fur coat. If I tell you it's not a cold day, can you automatically conclude that I do not wear my fake fur coat? Absolutely not. Okay. You can't conclude anything. Okay. So, first of all, we talked about this, I believe, last time. And second of all, on the diagram you can see it very clearly. If it's a cold day, in other words, if you're inside the cold day circle, what has to be true? You have to be wearing a fake fur coat. If you're outside the cold day circle, what has to be true?
You're not wearing it.
It could go either way. There's nothing that has to be true. You could either be wearing it or not wearing it on a not cold day. So this is, as you can perhaps tell, this is a very common sort of misunderstanding and misinterpretation. And if the only thing you do this semester is understand this mistake and never make it again, then you've actually learned something pretty serious and important. Sorry, which one? Okay.
Because in the conclusion it says all kids have favorite teachers.
Uh-huh.
Like you don't see the school anywhere in the conclusion. So why do we have the school in that?
But we okay, so to go back to the kids in school one, we needed school as part of the structure of the entire argument. Because we needed to know that the just to speak in terms of the diagram, the K circle was inside the S circle, was the first statement, and the second statement is that the S circle is inside the T circle. So then that allows you to make a statement about kids and teachers, because now you know that the K circle has to be inside the T circle.
So if the S circle wasn't there, that wouldn't be a diagram.
It would be, well, you said if the S circle wasn't there, but every single statement has something about school, so it would have to be a completely different problem. But to make our conclusion, we can simply say, what's the relationship between the K circle and the T circle? And what is the relationship? What's the relationship between the K circle and the T circle? Right. The K circle is completely inside the T circle. It's contained in the T circle. Therefore, in words, all kids have a favorite teacher. Okay.
Why the T circle is outside of S circle?
Mm-hmm.
I think it should be T circle inside of S circle. Or it should be school, or the teacher is school.
That's not what it says. It says everyone in school has a favorite teacher. So everyone in school has a favorite teacher. So in other words, everyone in the S circle, what? Is also in the T circle. Because everyone in school has a favorite teacher. So another way to think of this is, looking at the S circle, it says everyone in school. So let's shade it in so we see what we mean. Everyone in school is there. Right? Okay, so what are we saying about everyone in school? We're saying all those people have a favorite teacher. So all of that has to be inside T. You dig? Okay.
So basically it's like whatever the first statement is, it's going to be inside the second one. That's what I'm talking about.
I don't want to say first and second, because, for example, as we saw here, you can say if P then Q, and you can also say Q if P. So it's possible to move words and phrases around but still have the same meaning. So it's not always good to think in terms of first and second.
So whatever P is going to be inside Q.
But you have to know, what does it mean to say P and what does it mean to say Q. What you're saying is that if you have all of something is something, which one's inside? The all, exactly. And that's the logical connection. That's the way to think of it.
So
If the all is always inside, exactly. So in the first statement, it's the all what? Kids. And in the second statement, it's all what? What? School, exactly. Now, of course, it doesn't use the word all, but it uses what word? Everyone, which is basically a synonym. So, Terrell, that was a good question to figure these things out. Okay. Now, let's revisit these questions using logic notation. Okay. And just to make it consistent, I originally called this CD for cold day. So there we go. Okay. So let's do this last problem again using logic notation. On a cold day, I wear my fake fur coat. How can we rewrite that? What kind of statement is that? It's an if-then statement. If what, then what? So there you go. Now, let's see. I think let's do the first one first. So the next statement was, it is a cold day. So how do we write that down in logic notation? Yeah. Right. In abstract, we'd say P, but what notation are we using here? CD. Okay. So we know CD. So from these two statements, what are we able to conclude? Right, so the conclusion is I'm wearing my fake fur coat. And what's the notation for that? Right, the initials here. So that's draw a line here. So that's the conclusion. So this is a very, very basic form of drawing a conclusion. That's very fundamental to all of logic. If we have if P then Q, and we know P, then the conclusion is Q. And this is called the law of detachment, or in fancy Latin, modus ponens. So in this case, we say that Q is a valid conclusion because it is supported by what we know. Now, let's talk about the second one. The second situation was, on a cold day I wear my fake fur coat. It is not a cold day. So how do we write that down in logic notation? Not equals. Yes. Exactly. So we have this. So now remember, some people said, hey, we can therefore conclude not FFC. But as we just discussed, you can't say that. So if someone tried to say that, you would say that is an invalid conclusion. It's not supported by what you know. Okay. So in one sense we've already talked about all this stuff, but in another sense it's new because we're re-expressing everything in terms of formal logic. Okay. So far, any question about the first thing, making a conclusion using the law of detachment? If P then Q and you know P, then you can conclude Q. Any question about what's a valid conclusion in general, what would be a valid conclusion versus what would be considered an invalid conclusion? You ready for the next thing? Great. I own a computer. Some computers are laptops. Conclusion: I own a laptop. Exactly. Okay. So, is this a valid conclusion? No. This is not a valid conclusion from the things that we know. Let's take a look at what would be a valid argument. I own a computer. All computers are desktops or laptops. I do not own a desktop. Conclusion: I own a laptop. Okay. So good. All right. So I think you have the basic idea, or starting to get the hang of applying this rigorous logic to analyzing these arguments. So let's take a look at some more things. If it is a cold day, then I wear my fake fur coat. So we're well familiar with that. I am not wearing my fake fur coat. Yeah, you can conclude that it's not a cold day. So why does this make sense?
Because it's the if then, so if that's false, if that's true, then
Okay. So there are a couple different ways. So a couple people shouted it out. So there seems to be some sort of logic underneath that a couple people have tapped into, where it just makes sense. That's great. Let's also talk about this in sort of these more rigorous terms. There's two ways to do this. One way to do this is using an Euler diagram. So let's go back to the Euler diagram for this situation. So here's the Euler diagram, and remember what we were told. We were told that I am not wearing my fake fur coat. So if I'm not wearing my fake fur coat, where are we on the picture?
outside.
We're outside what?
Fake fur coat.
Yeah, that would mean that we were out here. So now what can you conclude?
It's not a cold day.
It's clearly outside CD, so it's not a cold day. So if you use an Euler diagram, the result should be immediately clear. Okay. But we can also think of this in terms of logic notation. What we know is that if CD, then FFC. But remember what we talked about last time. If we have an if-then statement, that's the same as saying what? The contrapositive. We spent a while working on that and figuring out that this is the case. So if CD, then FFC is the same as saying, so we also know not FFC. If not FFC, then not CD, because that's the contrapositive. But what else do we know in this question?
You're not wearing a fake coat.
Right, which in notation is what?
Not FFC.
Not FFC. So if we know this and we know not FFC, then what can we conclude?
That's not cold.
Not CD. Okay. Now, on the one hand, we're tempted to sort of reason things out using when you're presented with an argument, you want to reason it out using your intuitive understandings. Notice, however, that while our intuitive understandings are sometimes right, they're also sometimes wrong. We saw that with things like the fallacy of the inverse. So this is where logic comes in. It lets us analyze the argument in a way that, informally speaking, follows the rules. And we can be very clear about what's a valid conclusion and what's an invalid conclusion and why. So that's what we're learning how to do right now. is actually do this instead of just an informal, intuitive way, but is to actually analyze these things in a formal way, using very specific, always being able to justify what we're doing using rules. The rules that we should always be using when we're reasoning, but don't always. Okay. Now, this last form of arguing is called the law of contraposition, or in fancy Latin, modus tollens. So the idea that if you have if P then Q, and you know not Q, you can flip it around and say not P. I usually like to double check myself, and just sometimes I just like to write down the contrapositive just to make sure that I'm saying the right thing. Because if you have if P then Q, and if P then Q and you have not P, then what can you conclude? No!
If P then Q, then not P, then Q.
No. You can't conclude anything.
Right now.
Once again, this is the fallacy of the inverse. If I'm a baseball player, then I'm an athlete. I'm not a baseball player. What can you conclude?
Not an athlete. Oh, yeah, that's right.
Do you know anything about whether I'm an athlete or not? No, so you can't conclude anything.
Oh, so you can only conclude when there's a not Q.
Right, so if you have if P then Q, what would allow you to make a conclusion? If you're given not Q, then you can conclude not P. And also, if you're given what?
P.
If you're given P, then you can conclude Q. So on one level, you're obviously, this is a class, and we have an exam, so you're going to have to get this committed to memory eventually if you want to get these things right. But on a deeper level, I want you to understand this, and we're going to go through all the sorts of arguments like these, both in class and on the homework and such, and I want you to really understand and also apply this when you're making arguments. That if you say if this then that if you know that this isn't true, you can't draw a conclusion from that. Okay. So, next. I have a nickel in my... Okay, so first we talked about the law of detachment, which is modus ponens. This was the law of contraposition, which is modus tollens. So those are inferences using if-then statements, or drawing conclusions using if-then statements. Next. I have a nickel in my pocket, or I have a quarter in my pocket. I do not have a nickel. Conclusion.
You have a quarter.
Have to have a quarter. So this is the easy one, right? Okay. This is called the law of disjunctive inference. Okay, so to write it out schematically, N or Q, and then what else did we know?
You did not have a
In notation, not N, and the conclusion was Q. Okay, so so this fancy name I can actually give you a reason for. Disjunctive is just a form of the word disjunction. But disjunction, we talked about this last time, is just the fancy word for or. A disjunction is an or statement. And an inference, well, everything that we're talking about so far today is making an inference. If you know certain things, what can you conclude? A conclusion is the same thing as an inference. So it actually makes sense. So what I want to do right now is look at a couple of arguments and work on actually translating them, one, into thinking of them in terms of Euler diagrams, and two, also writing it out in terms of logic notation. And then I want to talk about if the conclusion is valid or not. So there's an Euler diagram. Alright. So here's the first one. All boxers wear trunks. Chris Mader is a boxer. Conclusion, Chris Mader wears trunks. So what can you tell me about this one? Okay. We're not going to say if it's true or if it's false. It's valid. Exactly. What we're looking at, and this is another thing that you'll have to get used to when dealing with logic. We're looking at the form of the argument itself. So we don't know whether or not all boxers wear trunks. We don't know whether or not Chris Mader is a boxer. We don't know whether or not Chris Mader wears trunks. But we're looking at the structure of this argument. So does the structure of this argument work? So we say, is it valid? Right. So for example, I could say, my name is Jason. Conclusion, birds can fly. Right. So now is the conclusion true? Is it true that birds can fly? Yeah, but is that a valid argument? No. So that's the difference there. So that's why when we're analyzing these arguments, we talk about whether or not they're valid or invalid, not whether anything is true or false. Okay. Or rather, the conclusion is valid or not if the conclusion is true or false. Okay. So, the conclusion is valid. So, great. So let's work this out. So, let's make a diagram and let's write this in logic notation.
Diagram is it's going to be boxes and then trunks. Boxes in one circle and trunks around it.
Okay. So boxers and then trunks around that. Okay. And that represents all boxers wear trunks. Alright, now what about the statement Chris Mader is a boxer?
It goes inside the B.
Okay. And I'll put CM. And so from this you can see that Chris Mader definitely wears trunks. Okay. Now how would we write this in logic notation? The entire thing. All boxers wear trunks. How could you write that in logic notation? If B, then T. Okay. What about Chris Mader is a boxer? Now I'll admit this one's tricky because you have to think of this in a way, you have to put this in words that we wouldn't normally use when talking about a person. So you could say that
C is B.
if you're Chris Mader, then you're a boxer. If CM, then B. Okay. So now obviously we normally wouldn't say it like that, but saying it like that certainly helps us see what the logical statement is. Okay. So from these things now, what can we conclude? CM, right, so if CM, then T. So if you're Chris Mader, then you wear trunks. Or in other words, Chris Mader wears trunks. And what argument is this like? We saw a similar example to this. Or what example that we've already talked about is this similar to? To the kids one, absolutely. Okay. Next. All Southerners speak with an accent. Bill Leonard speaks with an accent. Conclusion, Bill Leonard is a Southerner. So, what do you think? Valid or invalid? Invalid. Okay. So let's represent this with a diagram and logic notation, and let's talk about the conclusion being valid or invalid. So alright, so what does the picture look like? Sorry? Okay. So what's the first circle I should draw? Southerners. Okay. And then what's the next circle I should draw? Speaks with an accent. And where does that circle go? Okay. So does this tell us that does this picture tell us that all Southerners speak with an accent? Is it possible to be a Southerner? The way this picture is drawn, can you be a Southerner but not speak with an accent? Do you see it? Okay. So. Okay. So now we have represented that every Southerner has an accent. Okay. Bill Leonard speaks with an accent. So, sorry? All right. Well, actually, the thing is, where does Bill Leonard go? Okay. Do we know that Bill Leonard goes there? Where else could Bill Leonard be? He could be outside S as well. So this is precisely the point. Bill Leonard could be here. Bill Leonard could be here. We don't know. So can we conclude that Bill Leonard is a Southerner? No.
So for invalid conclusions, we can do that.
Exactly. Well, for this kind of invalid argument, you can't draw it because you don't know where it goes. Yeah. Okay. So now, how do we write this in logic notation? Okay. Right. So if S, then A, and
B is
BL. Well, Bill Leonard speaks with an accent. How do we represent that? Right. BL, then A. Now, how do we write down the conclusion in notation? BL, then Bill Leonard is a Southerner. How do we write that down in notation? If BL, then S. So now, what are we going to say about this conclusion? Invalid. Not false. It's invalid. We can't say it's false. It's Bill Leonard may be a Southerner. But so we don't know if it's true or false. But is what we just said supported by everything else that we know? It's not supported. So the argument and the conclusion are not valid. Okay. Alright. All contractors use cell phones. Doug Boyle does not use a cell phone. Conclusion, Doug Boyle is not a contractor. Okay. So why do you say it's valid?
because it's at all.
He's not a contractor. He doesn't use cell phones, so he can't be a contractor.
Okay. Right. So, in fact, for this one, I want to write out the logic. I want to write out the logic notation first. So, how do we write this down in logic notation?
C, if C, then
I'm going to use, let's see, contractors. I'm going to use CN and CP.
okay, FC and then CP.
Okay. So contractor then uses a cell phone. Okay. Next.
DB, not CP.
DB, then not cell phone, which is not CP. Okay. And so then what's the conclusion? If DB, if you're Doug Boyle, then not a contractor. Okay. I'm going to come back to that in a second. Now, what does the picture look like?
There's a little circle in the middle. There's contractors. And then
Okay.
cell phones outside. And then D is going to be outside of CP. Oh wait, no.
I should. Okay. Alright. I have to apologize. I've made this, I think, slightly more complicated than it needs to be. I think we don't really need to worry about Doug Boyle per se. We can simply say, so you could, let me just say, you could do it the way that I've written it. I've done a sort of more literal interpretation that is necessary. So, I'm going to do this, make your life easier. Not cell phone. So, yeah. Right. So let's just pretend that the entire problem is about Doug Boyle. We don't need to symbolize Doug Boyle at all. Okay. So, if you're a contractor, then use a cell phone. If a person is a contractor, then a person uses a cell phone. This person does not use a cell phone. So what can we conclude? Right. So the conclusion is that the person is not a contractor. Okay. Right. Exactly. Exactly. So the first statement, if a person is a contractor, then a person uses a cell phone, gives us this picture with one circle inside the other circle. Next, we know not cell phone. So not cell phone, if you like, tells us that we are out here. I've changed the grammar around to simplify it so you don't need this extra circle and this extra statement, this extra object to worry about. So now clearly what can you conclude about contractor?
Oh wait, which one?
Relative to contractor, what can you conclude? Right, but what's the conclusion?
That
Is the person a contractor or not? Can you say?
he's not.
Clearly has to be not a contractor. Okay. So, yeah. So, I'm sorry, I probably talking about the person as a set and a circle made it more confusing than necessary. It's correct, but it's not necessary. Yes, exactly. So we've used, you could say we've used the law of contraposition. Or another way to say it is that we've used the contrapositive and then the law of detachment. But that's what the law of contraposition is. If P then Q, and we have not Q, therefore not P. It's Doug Boyle would be outside the CP circle because it says Doug Boyle does not use a cell phone.
Yes,
Exactly.
But if Doug Boyle is outside the CP circle and the contractor circle is inside the CP circle, wouldn't that mean that Doug Boyle is a contractor?
So Doug Boyle has to be somewhere in the shading. So let's say Doug Boyle is out here. So what can you say about Doug Boyle relative to being a contractor?
Oh well, I don't know. So you can't go the whole way around, like around the other circles, unless this one is. Oh, not true.
Oh, all the way around.
Yeah.
So you're saying Doug Boyle is this? Doug Boyle is a whole lot of stuff.
Yeah, that's what I'm saying.
Okay. No, so what we're saying is that
He's-
completely outside of the CP. Doesn't contain CP, but is completely outside CP. Okay. So, right. So let me actually go back and revise the other arguments, so that they're sort of they're this simpler sort of thing. Okay. So you're a boxer. You wear trunks. This person is a boxer. Conclusion. Trunks. Okay. Next. You're a southerner. You speak with an accent. This person speaks with an accent. And the conclusion is that this person is a southerner. That's not valid. Okay. So notice what you were trying to do here. We're trying to say if S then A, and then I tell you A. Do you know S? No. Okay. And this last bit. All residents of Minnesota know how to live in freezing temperatures. Wendy Roxwald knows how to live in freezing temperatures. Therefore, conclusion, Wendy Roxwald lives in Minnesota. So, what about on this side? What do y'all think? Is this valid or invalid? Invalid. Okay. Exactly. Let's draw up the logic notation. So in logic notation, how does this go? So let's call being in Minnesota M, and living in freezing, let's call that F. Okay. So how can we write out the first statement in logic notation? Oh, you want to do the diagram? Okay, that's good too. Okay. So we have M, which is inside F, and then what's the next part? Well, it's not notation. It's just understanding what it says. It says Wendy Roxwald knows how to live in freezing temperatures. So what that tells us is that we're somewhere in the F circle. So does that tell us that we're somewhere in the M circle? No. Could be in the M circle, could be out the M circle, we don't know. So, invalid. Now let's go through the exact same argument using logic notation. So using logic notation, how does this look? What does the first statement say? If M, then F. And what does the next one say? That's the complicated way. So we're just saying F. Knows how to live in freezing temperatures. Now in notation, what does the conclusion say? M. But is this valid?
No.
This is not valid. Okay. So, yeah, sorry. Don't represent the person at all. Just pretend everything is about a person. So, if you're in Minnesota, then you know how to live in freezing temperatures. Next statement is, you know how to live in freezing temperatures. The conclusion is, live in Minnesota. That's not valid. Okay. So, any questions about this stuff? Okay.